Picture a gigantic spreadsheet. Every row is a person, every column is a movie, and each cell holds the rating that person gave that film. Here's the catch. Almost all of those cells are empty because nobody watches everything. The whole game of recommendation is filling in the blanks, predicting the rating you would give a movie you've never seen. Matrix factorization is the technique that cracked this open during the Netflix prize era, and it became the backbone of modern recommenders. Let's unpack how it pulls off that trick. The core idea is surprisingly geometric. Follow the sparse ratings table as it gets broken into something far smaller and far more useful. We start with that huge, mostly empty user item matrix. Millions of people down the side, thousands of movies across the top, and only a sprinkling of actual ratings scattered through it. Storing it raw tells us nothing about the gaps. The key move is to assume this giant table is really the product of two much smaller matrices. One describes every user as a short vector, and the other describes every movie as a vector living in the very same hidden space. We call the entries of those vectors latent factors. Now here's the payoff. To predict how much you'd like a film, we just take the dot product of your vector and the movie's vector. When your taste factors line up with the movie's factors, the score is high. When they point in different directions, it's low. One multiplication, one prediction. And where do these vectors come from? We learn them by fitting the ratings we actually have, nudging the numbers until the predictions match reality, usually with gradient descent or alternating least squares, plus a little regularization so it doesn't overfit. The magic is that once those vectors are trained, they let us confidently guess ratings for pairs the model has never once seen. To really feel why this matters, compare it against the naive alternative of just keeping the ratings as they are. Storing the raw ratings matrix is a dead end. It's enormous, it's almost entirely empty, and worst of all, it can't generalize. If a particular user and movie have no rating between them, the raw table has literally nothing to say. There's no bridge across the blanks. Matrix factorization compresses all of that into a handful of latent factors per user and per item. Suddenly, every user-movie pair gets a prediction, even ones never seen, because both sides live in the same compact space. It generalizes, and it laughs off the sparsity that stalls neighbor-based methods. So let's boil the method down to the three ideas that make it tick. Latent factor vectors sit at the heart of it. Each user and each item becomes a short list of hidden numbers, and those numbers quietly capture dimensions of taste, maybe how much comedy or how action-packed, that nobody ever labeled by hand. Predictions are just dot products. A rating is nothing more than a user's vector multiplied against an item's vector. So a single, cheap operation turns two little lists of numbers into a concrete guess at how much you'll enjoy something. Learning from what you know is the final trick. The vectors are fit only on the ratings that exist, then reused everywhere, which is exactly why factorization handles sparse data so much more gracefully than counting up similar neighbors. That combination of compression and generalization is what made it the winning idea of the Netflix prize era. Let's pull together the four essentials before we wrap up. Matrix factorization predicts missing ratings by approximating one giant sparse table as the product of two much smaller ones. Every user and item becomes a vector of latent factors, hidden dimensions of taste the model discovers on its own. A predicted rating is simply the dot product of a user's vector and an item's vector, learned by fitting the ratings you actually have. Because it compresses and generalizes, it handles sparsity far better than neighbor methods. If breaking down ideas like this is your thing, come explore more of them with us at standarity.com. We'll see you in the next one.